Hi, my name is Stuij. I'm going to present to you with a talk about the Game Boy Advance to make a toolchain for it. Actually, it's also very much about how to build an embedded toolchain. Some things that we're working towards is seeing what kind of issues we're seeing with DCC compatibility and also what other issues are currently swirling, because embedded is a hot topic, I think, in LVM right now. We're using, obviously, a Game Boy Advance toolchain for this, which is currently based almost on the LLVM, except for the C library. And we are basing this upon the LLVM embedded toolchain for ARM. I work for ARM, by the way, and the team that I'm in is developing this. So I'm kind of I'm on two sides of the equation, so to speak. It is open source. You can find the embedded toolchain is open source. My repo is open source. It's got a first release. It's obviously this is mostly just a toy project for me. It also includes these slides. The slides are basically a tech demo to see for myself if it works. And it works, which is nice. So some of the talk will be on the bare metal toolchain. Some things are going to be more Game Boy Advance specific. And it's meant to be a general tutorial. So it's not necessarily meant to be something that is focusing on the LLVM embedded toolchain for ARM, which I'm going to call BMT because LLVM embedded toolchain for ARM is a mouthful. Bare metal toolchain, by the way, BMT. Okay, a little bit of an intro about myself because I've been since long been I've been quite obsessed about the Game Boy Advance. I started my somewhat significant programming on the Game Boy Advance. I made a book reader, that was my thing at the time. On this screen, I read so many books. I don't know how I did that. Anyway, it got a couple of programming jobs for me. So I follow where the Game Boy Advance takes me. It's my guiding light in life. Let me see. So obviously I work at the embedded team, and I wanted to make an LLVM-based toolchain, but at the time, things have changed a little bit. It was somewhat hard to find information on it, and I had other things to do. I sort of let it go. Once we started working on the bare metal toolchain, it was the perfect reason for me to get back into it and program for this. A little bit of overview on the talk. So after this, a short history on where embedded is in LLVM. A little bit of an introduction, or for some people, a reintroduction into the Game Boy Advance. We'll do an example program, and we've got an example program. We're compiling it or showing how. We're just slowly building it up a little bit, or that's the idea. We'll do an overview of these components and build setup. We'll work the gamut, and at the end, for funsies, optimization, because it's actually really fun to do optimization on the Game Boy Advance. This is my sort of title setup. Let me see. This one needs to go back. Here, this is how I figured it. We're not done yet. Yeah. The fact that sound works is an indication that the toolchain works, because sound needs a couple of things to work correctly. We'll go into that a little bit maybe later. Go away, Dragon. Okay, a short LLVM embedded is very, very short. So LLVM has, of course, concentrated mostly on hosted systems, and embedded toolchains didn't get much love. There was an implementation for ARM that somewhat worked, somewhat didn't work in certain points in time. I feel, and that might be debated, in 2020 things started to heat up a little bit. Hafiz Abid Kadir did an LVM talk about the risk-free toolchain that he made. And since then, we've got RISC-V, we've got PowerPC, we've got AR64, and that's nice. But also, there's a lot of discussion around embedded these days. So we've got monthly meetings for the LLVM embedded toolchain working group, and a lot of interesting things I think are being discussed there. Some of which I'll touch upon. A little bit of overview on the Game Boy Advance. So the chip, ARM7 TDMI, its claim to fame, I guess, is the thumb instruction set, which is 16-bit, but still uses the 32-bit registers that we have come to know and love. This is about, actually, I kind of know this is in the end of 94. I think 94 December when it was officially released. It did very well for itself. It became immensely popular. It was somewhat popularized by Nokia, which also had a lot of success. But actually, the thumb part of it was thought up by David Yeager, an ARM employee, on a trip to Japan, where they needed to figure out something for Nintendo, who wanted, or was it Sharp? I'm not really sure what the discussions there were. Who wanted 32-bit instructions, but they didn't like the size blow that came with it. So a little bit about the Game Boy Advance itself. So it's got a picture processing unit, as Nintendo calls it, somewhat of a 2D GPU. It's got certain modes that it uses. It's got bitmap modes where it addresses pixels one at a time, and you can color them. Or you've got tile modes where you manipulate 8 by 8 little tiles that you can move around the screen, and you can reuse them. And it's a hardware speed up in its space saver as well. The original Game Boy comes included with the Game Boy Advance because you can play original Game Boy games on it. You don't have access to it as a developer, except for the PSG, the sound chip, which has a couple of waveforms that you can manipulate, so you can square wave them and whatever. Next to that, it's got 2 sound channels to convert samples, your standard PGM samples. You throw them into a DAC, into a FIFO that feeds into the DAC, and you need the FIFO, and that's a hassle. And also the great thing about the Game Boy Advance, it's sort of the last of the Mohicans, I guess, where it's you manipulate I/O registers straight, and it's just a really fun thing to program for. Also, it's got a bit of a wonky memory setup, and I'll get to that later. A quick example: you've got your main, you draw something, you spin on a while, which you normally would not really do. But anyway, so what you would do is you manipulate this rec this display control, and you turn on bitmap mode, one of the bit modes. You turn on a background. You've got 4 backgrounds, and you're using number 2 at this stage. And then you were using, so there's something called VRAM, which is video RAM, which you manipulate, and video RAM does different things depending on what kind of mode you're in. For this mode, it basically uses it as a half-word array in which you can poke colors, and that's what you're doing here. So here we're just looping over VMM, and we're chucking in colors, and it paints the screen 31, which is red. Switching over to Toolchain. I thought I'd go over the components first, which you would typically need for this kind of toolchain. So of course you need a compiler suite, and you'll need your compiler RT built-ins. So this is code that you need for that a compiler will spit out that you need to link in for platform-specific routines. libcxx we're using. as the libc++ library. We're using picolib for embedded for the C library. Then you need a linker script, you need startup code, and then you need some Game Boy Advance specific things, like homebrew scene things. Like the standard for homebrew work is tonk or libtonk, which basically defines like all of these memory mapped registers and gives you like a number of helper routines, like for example for interrupt handling and that kind of stuff. Also, you've got a music library and basically how, like at least in open source setup, how you're doing music is kind of like how you're doing graphics. So what you have is samples. You're using the mod format. I don't know if you've got some graybeards that love Amiga coding and have used the mod format, which is basically you've got samples, you put them on a timeline, and like that gets encoded in some format on the Game Boy Advance, and then basically the code reads the timing, and at the specific times it pulls in the samples and it will play them. You've got Grid, which is a sort of slicer wrapper of graphics. So you've got your BMP that you can use for backgrounds, for example. So this background that you're seeing here, this is actually a tiled background, which I'm just like sewn together to make a contiguous display. And then you've got just fixing up headers. So headers are defined in the startup code, and you want to at least fix them up with a proper CRC that the BIOS will check. This is typically how you would compile a program. So you slice and dice up your graphics, you convert your sound data, you run Clang over all of this, and then you mash a binary out of it. You strip the ELF for binaries, and then you fix up the header. Just to be totally exhaustive, in the config file, you've got your targets. We're not using exceptions. We're not using real-time type information. You need to set your sysroot, which I'll get to. You need to specify your startup code. And then this is quite recent. I tripped over this a few months back because now we're doing verbose aborting in LLVM. And embedded platforms don't like that very much because they don't know how to handle printing stuff out to some kind of display. So I turn it off like this. I'm sure there's a better way, but this was the easy way for me to do it. The way that like a pointer. So the way that we lay this out is obviously if you've got like your Toolchain, how do you say, like your directory structure, you obviously got your bin where you put your compiler tools. I chuck in the Game Boy Advance tools, and you've got that Game Boy Advance config file. Then you've got where you chuck your libraries, your specific libraries in is this path. It became a standard at some point, I think, because of the work that the before mentioned person put it there. You've got your lib where you put in your startup code, your LD scripts, and your libraries, and your headers obviously in your include. And you've got this Multilib YAML file. For embedded, you want to do Multilib in some way. I'll talk about Multilib later. Right, dependency graph. It's a hint to me. I missed the timeline. I made a beautiful timeline here. You can see the difference between the Game Boy being emitted and the Game Boy Advance. It's a very long stretch of time, and Nintendo was in talks with ARM in '94, but it just took such a long time because the Game Boy did so well and it basically didn't have any competitors. Right, where was I? Where's my mind? I thought nostalgia must hit people. I thought I'll show like a big thing of these. So the way that you structure all of this stuff is other people have done. So I recommend Peter Hosek's talk on CMake. He goes into this in much better detail, and in general, we'll get to CMake. But anyway, the way that we need to resolve dependencies in some way. Game Advanced, like general host tools, they stand on themselves, of course, plus config files. Then we've got our like standard compiler tools. So you build your targets for your you build your compiler tools for your targets. Your C libraries are obviously like everything else is dependent on your compiler tools because you need to build them. There's a circular dependency between these because if you want, for testing at least, because if you want to run your C library test, you need to have this compiled. So like this is at some point resolved. You build your test after you, obviously you build this. But like there's a bit of circular dependency going on here in general. So there's your lib and winds, and often you just need the headers. You don't necessarily need to build your stuff, but implementation. You've got your lib unwind, which needs compiler RT built-ins. You've got your libcxx as well. You've got your libcxx ABI, which I'm pretty sure only needs the headers of these. And then libcxx, when you're building, needs libcxx ABI. Luckily, like this whole stretch, we don't care about it. Wrong thing. Because we've got our runtimes. We're kind of stuck on compiler RT built-ins. Again, like check out Peter Hosek's talk. He goes into that stuff in more detail. You've got your runtimes. We feed our variables to runtimes, and it will figure out all of this, which is quite nice. Okay. Where are we? Yes. So you've got your. Now we're going to building. So we want to build this in some way, and we are going to use CMake for this. The BMT, our bare metal toolchain. Uses, like at some point they didn't use CMake. At some point in an iteration we were using Python to do this. At some point like it was too slow. We said scrap it, we're going to use CMake because it's much more efficient. I think it makes a lot more sense as well. So we built our toolchain on top of the BMT. We use CMake. It's all, yeah, it's in some way it's quite nice to work with because it is so composable. The way that's like BMT does it, and like my little toolchain as well, is that we first download all our dependencies. Then, like for LVM itself, the LVM target, it's a sub-project. That is a CMake concept, by the way. Then we do external project add, which creates a target for the runtimes, for the compiler RT, for picolibc, and then we feed those CMake arguments to stay sane a little bit. And then once we're done, then we compile our GBA libraries with like the full toolchain that we eventually made. And when we do our library variants, we just loop, and I'm sure there's better ways. And I saw again, like the Peter Hosek talk seemed to point that there's nicer ways to do this maybe. But I guess I should have a talk at some point. And general tips, just piggyback on everything that LLVM does. So CPack, for example, is packing up things into a shippable package. Like testing works out of the box. Like all the infrastructure for all of this works nicely. And you're just gonna have some headaches sometimes with mixing up things that you put in, like that you haven't like sanitized properly for the target. Like you might leak host information to the target, which then gets picked up, and that can be a pain. And what I suggest, use something like the BMT as an example. Like I could not find any other open source toolchain that you could just learn things from. There's Pigweed. I looked at it a little bit. It uses GN, and I just could not figure out so quickly. I just did it when I heard about it yesterday. I just could not quickly figure out like how it would all fit together in a way that like is pleasant to use for, as an example. And maybe there is, but this is one of them, and it works for me. CMake argument theme. So as I said, like at some point, like you need to chug in CMake arguments to these different projects, and I think there's like a couple of things to look out for. First of all, again, like use this example, because like figuring this out for yourself is a hassle, and you can see what you need and what you don't need. But there are some themes here. So first of all, you need to set your target in some way. You need to specify that you're building for embedded, and like this works in like a number of different ways. Like you need to set static libraries. You need to like bare metal blah blah on. Like there's a number of ways. There's a number of different named things that you need to put bare metal in. CMake system name generic. At some point, like there are other CMake variables that you set to make sure that you know that you're building for a target and not for the host. But for OS X, at some point we had issues with that. This seemed to help for us. And just an example of stuff that you need to chuck in there. Again, like your static library, you've got a whole bunch of like options that you can turn off for your standalone compiler RT that you're going to use to build the rest off of. You need to turn off sanitizers and all this stuff. And at the moment, we're not using it for embedded targets. You set your targets. You set your tools, as I was talking about. You set your bare metal build to on. Set default target only, so it will only build for your target. And like at some point, like again, like we're looping over our different variants if we need to. And then like setting up certain things for the build. Basically the same with runtimes. I'm not gonna. There are so many options to set for runtimes, especially. It's three things that you're building at the same time, and a lot of them look alike. One thing to note is set compiler RT to on, so it will actually use compiler RT. Tell it to use Unwinder. Let me see. I don't think this adds very much. Okay, moving on. I'm gonna talk about individual components that you eventually need to build, and like issues that I ran into with like my specific toolchain, and things that are hot topics right now that people have been talking about. First of all, Clang. So this is not an LLVM talk, example talk. Like LLVM is compiling for much weirder architectures. ARMP4T is Thumb1. It's very well understood by the compiler, which is nice in this case because we care. I think people care about like the exceptional cases that they need to look out for. Even though great project that. Fun fact, for ARM, Clang actually defaults to ARMP4T, and also it defaults to ARM7 TDMI if you don't put in a specific architecture or CPU. One thing to note, like Clang-wise, the exciting stuff happens mostly, not just, but like mostly in bare metal.cpp. And it handles things like, for some targets, Multilib and NoSTD Inc. inclusion. Issues that I ran into with Clang is like LLVM wasn't really around when we cared enough about ARM7 TDMI. Like the assembly syntax that we used to use, that a lot of these projects use, these open source projects, that you can still compile with DCC, no problem, with just minor differences. This syntax doesn't exist for LLVM, so it uses a more modern syntax, and at some point I thought like, oh, I'm going to hack in like the old assembly syntax. First of all, it's a hassle, and maybe it's not the right thing to do. So just change your source code, I would guess. A lot of these moves need to be move S's, like the ordering of these kinds of instructions. Like this here and this one here, like we turn them around. There's no long call function attributes. We don't care so much about long calls anymore because we do that in the linker. No and thumb interworking because the modern ABI that we're using right now doesn't care for that as well. We're doing that by default. And like this is an up on GCC as well. Multilib issues. So for embedded targets, LLVM for a good long time didn't really have a very good answer to mapping how do you say the target that you're now building for to the libraries that you want to use. Like people would hardwire it into their C++ code. GCC has other options. Well, first of all, like it will build a toolchain per target, but also it has got spec files that are fairly complicated. Like we looked into at some point to using spec files, or maybe a subset of spec files. We didn't end up going with spec files. We went with another solution, which is we're trying to be a bit more flexible. We're trying to be a bit more declarative about it. So what we're doing is we're trying to normalize command line arguments. Like as some of you here know, LLVM and command line arguments is a bit of a horror show sometimes. So what we're trying to, so for example, if you've got, if you define dash mart is X, we'll put that in the target, for example. And then we've got this multilib YAML file that you saw before somewhere. Maybe I shouldn't go there. Yeah, here, multilib YAML file. Where are we? Oh, we ran too far. Oh, we went way too far. Did we go back? Yeah. So what we're doing is we're defining the library variants, and then we're defining matchers. So the library that you're trying to work for is sort of connected between your matcher and your variant. And that works out pretty fine, I think. And like we're adding features like composing, like if you're matching multiple variants, like you can, for example, like put both of them on your linker path. If that's something that you want, yes or no, that's another question, and that's a little bit up to the toolchain to see how they want to use this infrastructure, or I mean your specific target. What didn't work for this didn't work for the Game Boy Advance because of a tiny bug. When you define that you're gonna compile for thumb, it will put that into the target triple, which we weren't ready for, but you can change that with your matcher rule. Linking is interesting on embedded targets. I think like you can see like that's like a big like divide between I got enough time between like linking needs work, and linking is it's a place where you do different things in your embedded context than what you're doing with your hosted context. So I broke this up a little bit. First, I'm just going to talk about the Game Boy Advance memory region overview because it's handy to explain some linker concepts. I'm going over embedded linker, the embedded linker setup a little bit. Not everybody might be familiar with that. I'm going over linker issues and again, what's hot in the linker space. What are we talking about? Again, go over this one. Right. So this is basically your memory setup. You've got your CPU, which is connected to 32-bit. I thought about like patching up this to make it more readable. I couldn't bother. So this is connected with a 32-bit bus to your internal working RAM, as it's called, in Game Boy Advance terms at least. and that is your quick memory. It's the only 32-bit bus that it has. You want to put your fast code in here. So you want to put your sound code in here. So again, like sound sound handling in the Game Boy Advance is very basic. It doesn't really have like a proper chip for it. So you need to do the mixing. The CPU needs to do the mixing of the music, of the different samples in the music, of sound effects, that kind of stuff. And music is continuous. You need to do it all the time. So you need to dedicate some effort into that. Like Apex Audio System like takes up, it depends, like between 4 and 10% of your CPU time, depending on like how crazy you want to make it. Then you've got your VRAM that I talked about for your video needs. You've got your external working RAM, again 16 bits, which is you use it for your data and for your manipulation of things, your stack. It's got like a little prefetch buffer. So what happens if you access ROM? It will take the next instruction as well. And it's a 16-bit bus. And sometimes I wonder like how much on purpose is this, just to also make sure that you're using your thumb code, because you can't use ARM because like it will need to fetch twice to get the instruction, and it will lose out to thumb codes here. Then it's got an 8-bit connection to it. This is basically where save files are stored. Very slow, but it doesn't matter because you need to like write just a little bit to it at a time. So in embedded context, how all of this works, it's fairly simple. In your link script, you define what pieces of code you want to put in which memory regions. You do that by defining sections, and you put those different things in those specific sections. And then your startup code knows the name of those sections, and it has like little routines to copy the data over. It will do your standard initialization stuff. It will initialize BBS to 0. It will start up your C++ library stuff, and then it will call into main, and that's it. It doesn't care about exiting. Things that were issues for the link. That was basically like the thing that I had most that actually needed a little bit of coding. For ARM v4t, LLVM, you couldn't do long branch, and you couldn't do ARM-TOM interworking properly. So basically, the linker was broken for ARM v4t. Because those routines used BLX, which is branch, link, and exchange, which doesn't exist on ARM v4t. And it doesn't have move v and move t for instantiation of variables, for instance. So I needed to write some thunks or veneers, how you want to call it. But it's pretty easy work in the end. For the Game Boy Advance specifically, it uses basically the linker script of the GCC standard dev kit. It has been going on since, I don't know, 2000 and, I don't really know, 2002, 2003, something like that. Still going strong. Things that broke for me was LLD didn't accept the overlay syntax that this linker script has that like currently nobody uses. Like LLD does do overlays, but like it looked to me, like looking at the code, it just looked very very simple. So it in general, like we know that it needs work. Anyway, some C++ data structure, some code sections needed to be put in the right place, and we didn't define the right names for those. There was some CLib incompatibilities with things that were defined in CLib that we didn't know how to handle. Very, very small potatoes, quite easy to fix up. I'm charging on, 14 minutes left. Linker improvements. So in general, things that are hot topic, LTO everywhere a hot topic. Also in the embedded space, embedded and LTO don't like each other very much. You've got as you can see here, obviously you've got all these weird memory regions, and LTO doesn't necessarily know how to handle that. Code size can worsen, as I understand. In some cases, it can do nothing at all. Work to be done. There's been talks at the dev meeting here to see how we go forward. There's a couple of proposals on the table, and hopefully we can pick one of those and move forward properly. Another thing is distributing code. So if you've got, for example, two memory banks of equal functionality, you just want to distribute your code over them if you can, instead of doing that kind of stuff manually. For the Game Boy Advance, it doesn't matter very much, I think, because all of these have very specific functions. But a lot of other systems could use this kind of stuff. Things like automated compression and decompression of your code and data would, I guess, be nice. Debuggability in different ways. LLD is just not up to snuff with DCC, who has a lot more functionality for that kind of stuff. Things like calculating what your stack depth could possibly get up to. It's not perfect, but some toolchains try to do some best effort in that regard. And some other things, placing sections in, for example, your memory mapped I/O. If you want to populate it with on the Game Boy Advance with some presets, maybe that would be nice. Automatic overlay management. I guess there's a gradation of that, but LLD doesn't do that at all right now. Yeah, I think that's it for LLD. Quickly moving on, compile-RT. As I talked about a little bit before, we've got your runtime support. We've got our built-ins. We talked about that previously. I think we're hopefully somewhat clear about what that is. It's meant to be a libgcc replacement, and it worked for me, basically. Almost. Well, I'll get there. It mostly worked for me. Compile-RT is more. It's also sanitizers. It's profiling support. It's fuzzing support. A bunch of other stuff. We don't build them currently. Some people are looking into getting this stuff working. Profiling is another topic that has been broached in the monthly meetings. For ARMv4T, there was no built-in target. So yes, there was actually a little bit of an issue, but it was easy to fix because it basically, compiler-RT built-ins basically means there's a bunch of different files that define things like atomic handling and thumb1, thumb2, that kind of stuff. So it was a question of choosing the minimal set of files for my target, and that was enough. And after that, everything just worked, which is nice. One thing, well, first of all, Edward sanitizers. Actually, somebody from my team did a hacking day project, hacking week project to get ASON working. He got a prototype working that sort of separated the shadow memory from the code that it's attached to put that, for example, in RAM instead of the code that might be in ROM and stuff like that. I mean, it's pretty hackish. It's not actually production quality, but it's fun work, I think. One thing that you get practically for free is undefined behavior sanitizers. You can set this, I guess, how do you call it, trap mode. So you can ask it to just fire up a trap for you. I tried it on the Game Boy Advance, and that did not work out very well because in the beginning there was an issue with basically what it will do. It will just try to run an undefined instruction, which will trigger an undefined instruction exception handler exception which would go to a handler. But for the Game Boy Advance, like you're basically locked by the BIOS. You don't have access to setting the exception vector table. Like reading the BIOS, it turned out that this goes to an exception handler that will go to a specific piece of memory that is meant for debugging, for the debugging toolkit of the Game Boy Advance. So I couldn't use that, but luckily there's you can override what you're going to do with like this specific trap. So you can give a function to it. So for the Game Boy Advance, that works, and this is a demonstration of that. So basically, we trigger over here. We trigger going past the array, and there's like a little bit of instrumentation code that checks if this is the case, and then it will fire up this exception handler, which is at the end of your function. And so if you come back from your exception handler, you're toast. But that's fine. Yeah. We'll move on. How much do we have? Oh, good on time. We move on to CLib. There's a question for embedded toolchains. Like there's a whole what CLib are you going to use? There's nanolib. There's newlib. There's newlib nano, which I think ARM made at some point, which is a newlib for a bit more embedded use cases. We've got picolib-c, which is newlib, but a fork of newlib. We've got LLVM-libc. We've got a whole bunch of others. Which one are you going to use? At some point, we went with picolib-c because, like, a bunch of reasons. Newlib's licensing is a little bit of a mess. It's got a whole bunch of licenses, and so you're beholden to all of them if you're not going to like cut stuff out, which you can. Newlib doesn't have an LLVM config. It worked out. It had a nice responsive maintainer. Maybe that's the same with newlib, but it worked for us. And it seemed more suitable for our kind of embedded development. There's also LLVM's libc. So yes, like it just sounds nice in general, of course, to use, and it's got nice properties to just use LLVM all the way. I guess you feel like you're more in control of the stack, which looks really nice. Like again, like there have been talks with the Google people that work on this, and they can compile for their use case pretty fine. For embedded, as I understand from them, things seem to work out quite nicely. And there's always talks, I guess, on like how to like. The embedded space is so heterogeneous. Like lots of different use cases need different ways of their tool chain, and how we're going to do all of this. There's some other issues as well. Anyway, for the Game Boy Advance, the big hot topic is just a minor one. We need to implement like some kind of like output. So there are some like convenience functions that are useful for debugging and for just quick hack and slashing for the Game Boy Advance. Normally you wouldn't use this, but yeah. Moving on to libcxx. So we're using the LLVM libcxx libc++ library. Not too much to say on this. Maybe there's again talks about making it more efficient for embedded. There's talks about, or like the Google people, I believe, have been trying to like carve out certain functionality that you need to be using. Looking into like people have been looking into like just distributing it as source, so people can compile it like the way that they want and use it in the way that they want instead of like just using the binary. For the Game Boy Advance, I think in like the biggest use case for libc++ is an engine called Butano from the gas things, and they're using ELT, which is basically sort of a cut down libc++ for embedded use cases. LLDB works, which is nice. It works with, well, it doesn't work with your hardware target, but it works with MGBA, which is, I guess, like the most popular emulator these days. It needed some work. Shout out to my colleague David Spickett, who did some work in this area. Like it fixed some MGBA things to get this to work. It also works with VS Code. There's he made a document to show like how this stuff can work. You either use Code LLDB, which is a VS Code plugin, or you use LLDB VS Code, which is actually built within the toolchain itself, which is supplied with this little toolchain that I made. Not much to say. It works, and that's all you want for. I haven't test driven it very much, so I don't know how well it functions. We're gonna skip over this. Gamer advanced tools, a bunch of them. One thing that has been fun is how well does it actually perform. So I ported Coremac to the Game Boy Advance, and I checked out what the Coremac scores are for it. Just to give a little bit of a heads up, the Cortex M0, which is a very minimal processor, has a Coremac of 2.33. So Coremac is basically iterations of Coremac per second. Coremac is a very small benchmark. It's meant for an embedded use case. So it fits in IVRAM. It advertises to be 16K. I haven't really checked out like how much it is on LLVM exactly. Cortex M85, 6 point. Oh my god. Maybe I'll run over for 2 minutes. Is on 6.28 Coremac, and if you've got something beefier for mobile phones or whatever, it goes up, of course. Let me see. So this is what it looks like on the Game Boy Advance. So this is GCC. This is Clang. Both seem to work. I made a little table here. This is just, it's fun to look at how these different scenarios work out. So if you put your code in ROM and if you use ARM, it's got a Coremac score of 0.377, dog slow. Thumb, a little bit better, also not very quick. Then you, of course, you're chasing DCC as Clang. So Clang does a little bit worse. It does worse. More worse for Thumb than for ARM. But if you start to turn things on like jump threading, the event jump threading, or you put some other things on like tweaking, inlining, and that kind of stuff, all of a sudden things go a lot quicker. So we're moving into IWRAM, Thumb, it jumps up. Not surprisingly, all of a sudden you got a lot more to work with. You go into ARM, we're getting close to this target, and yay for if you put on like a bunch of more optimizations. We're hitting Coremac score of 2, up to 4, I would say. That's it. Some resources to look for. Discord, LLVM has got the embedded toolchain channel. Discourse has got a working group page in which we always put the notes, very informative. If you want to do game advanced development, use gbadev.net, it will set you up. Embedded toolchain here, and some Multilib stuff. That's it. We got here, yay.
That's awesome. Thank you very much. We have time for a couple questions. Please come up to the microphone on either side and ask the question if you have one.
Awesome talk. Very, very creative. Creative use of Homebrew for the talk itself. Then a comment and question, or that was the comment, but the question is, can you tell us a little bit how you developed these slides? Were you presenting from the Game Boy, and how are you doing video capture, and how did you make these slides?
Yeah, yes, okay. So you can buy, aftermarket HDMI. This is, so you can see here, you can buy like these cards, like this is a very El Cheapo card. which
Custom
is
shell on there, nice.
yeah, exactly. Handy to see. Which has got an HMA out. I should have told this. Like I did a presentation internally in ARM. People said, "Are you actually doing this?" Yes or no? Yes. Shout outs to the AV department. They did some good work to actually make it work because yeah.
And any info on the slides? How you did the slides?
So yeah, the slides are up on GitHub. So it's just standard Game Boy Advance development. So using like this low-level library libtonk, and like using all these tools that I've been talking about to slice and dice like all this stuff.
Cool.
Yeah.
Thanks.
So a few slides back, you talked about you had worse code size on LTO. So like I was wondering, like you had more details what you tried.
Right. So actually, code size for. Oh, by the way, I wonder if this stretched QR code is going to work, yes or no. But where were we? So for basically. Both of them generated 20, like the total ROM size was for ARM, I think, 26K. So GCC and LVM was basically the same, if that is what your question was. Like if you're adding some of these like optimizations, like if you do like total loop unrolling for LVM, it exploded. It went to 140K. So that didn't work with IWRAM anymore. Like all of like the 3 different optimizations that I put in here, like jump threading added 1K.
But that's like without LTO, is that?
Oh, this is without LTO. Yeah.
Without LTO.
Yeah.
Like with LTO, like did you try? Were you like compiling for OS or Z or something like that? Like minimize code size. Did you like using full LTO, teen LTO?
Oh, nothing. No, I did not have it. I did not have the time for like a lot of this stuff.
Yeah.
So you can see here. No, wait, I'm bumbling. Here you can see what the compiler flags were. So just O3, and then like a number of these optimizations. Very, very basic.
Okay.
To be continued with like all of the delving into like what's going to work, yes or no for this.
Hi.
Hi.
Great nostalgia trip. So
Right.
20 years ago, from SM Systems, I worked on the original AGB toolchain
Right.
and development kit. So just wonder if you did any research in terms of the toolchains and the dev kits back in the day and how it compares.
So well, a little like the open source community, like what I read myself is there's just not a lot of information about it. Like, for example, like we know that at some point a CD went out with a GCC version, which is maybe yours.
Yeah.
And then I know that I just had like a nice talk with somebody from Nintendo about like what they were using. And so they were actually using the ARM AC5 tools for development, and what they sent out to like a bunch of partners, I guess. Like that's what I know.
Yes, it's all a bit hazy.
Yeah. But like I'd love to talk to you and like a bunch of others, like to see like how this stuff worked. I'm quite fascinated.
Have to chat afterwards. Yeah.
Yeah, nice. Yeah.
Great. Thank you.
Okay, thank you very much, Dees.
Yes.